we keep going, because what we're going to do in a second, as you can see, is we're just going to come up with a bunch of rules and not look at the limit anymore. The limit is the conceptual part of the derivative. And if you've taken calculus in high school before, you might not really get into that limit derivative very much, or the limit definition. We really kind of emphasize in college because we're trying to, have a deep understanding of this stuff. But what the next page sort of says, and you can just see what it says right here. We learned how to calculate the derivative using this function or the other ones. But these things, you can use this to derive the below rules. And so instead of having to do a limit every time, right, we just know that we can just follow these rules because these rules follow from this limit definition. That's what I'm trying to say. Let's see here. Do we do reactions? We do. I'm just curious, how many people took some version of calculus before in high school or some other time where they're kind of familiar with, for example, the power rule? Is anyone familiar with any of this stuff? And if you are, maybe just raise your hand or put a thumbs up or something. See how I'm doing that in the chat? I'm just curious if this is brand new to some people or everyone, or if there's a couple people seeing. Okay, great. Only maybe a couple people have thumbs up. Wonderful. So if you are, great. Now we're getting into something that maybe you're familiar with. And I'll just say again, if you're not familiar with this limit definition, it's just because a lot of times in high school we don't go in deep into that. I recall in high school, it's like the kind of thing that your teacher kind of shows you. Maybe you did an example, but it's not the kind of thing that you might see in homework and things. And here we're doing it in the homework, and then we're moving past it into this stuff. Okay. So, and some of the homework this week is based on this stuff. So I'm probably going to fill out the rest of the period here with a few of these rules. So notice there's a lot of them, right? There's a couple of pages of them. This is the kind of thing that you want to have sort of out and reference. And paging through people's notes, it looked like almost everyone printed the notes out, which is great. And what I would suggest is this particular page, does it fall on, I hope it's not between pages or not. But anyway, you might just want to have this sort of out separate from your notes as a reference. I always come back and reference this page, or I'll try to at least. And it's a good idea if you had it referenceable too. And again, the idea is we apply the limit definition and we get these rules. So for example, and let me sort of set up the page. So on this page, all these things are constants. So C, B, M, N, A. Like here's a C, here's an A, right? Here's some of the other ones. Here's another C, here's an M. All those things are just constants. And so the only thing that's a variable in here are the X's. And what's going on here is it tells us the form of the function in the middle column, and then it tells us the derivative in the right column, right? So notice how here we have f of x, and here we have f prime. And so the right-hand side is the derivative of that one. And so what the first one tells us, this is the most basic rule there is. This is what the homework's on this week. It's the power rule. It tells us when we have x raised to the power of n, when we take the derivative, you just bring down the power n and subtract 1 off the power. See how that's what that says? Let's do a quick example of that. If our function is, for example, x squared, like we just looked at previously, we found that the derivative of that was 2x. And here what we're seeing is that rule in practice, right? The derivative is bring down the power, subtract 1 off the power. That's what this rule tells us to do. And so we get 2x, just like we found previously, right? We just did that a second ago up top, and I think it's worth at least kind of sliding back up to that right here, right? We just did that right here using the ugly limit definition. It was a whole bunch of work, and what I'm saying is, hey, we have a rule for that now. We don't have to do the limit definition anymore. We can just use the power rule if we want to do something like that. We just bring down the power, subtract 1 off the power. Right, and there's a little 1 right there, technically. Is that okay? See what I'm saying there?
I follow what you did, but like, what's the point of that? That's the.
Let me put my hand down. The point is, if we want to take the derivative of something raised to a power, like this one, like this one, right? This is an example. This one right here was an example of a function raised to a power, x squared. And we did all this work with the limit and we got 2x. And what I'm saying now is we don't have to do the limit definition anymore. We just know we bring down the power and subtract 1 off the power, right? So if we had x squared plus 1, it turns into 2x without doing all this intermediate stuff.
Cool.
Right. And we did the example, right? We did that one here. And so hopefully you saw how that worked out the hard way. And I'm just sort of saying, okay, we did it the hard way. Now here's the secret rule that we can use without and to avoid that stuff. And the weird thing is in the homework this week, you're going to do both of them. You're going to like struggle through doing it the hard way, and then you're also going to do it the easy way. Sorry, what was someone going to ask?
I was just gonna ask a quick question. On the example we looked at, it was x squared plus 1. Does it matter what the b is, what the plus b is, or minus?
Yeah, good question. So that's actually the second rule here. Let's jump right into that. So that's the constant rule. So if the second one says if we have a function that's just a constant number, when you take the derivative, you just get 0. And so in the example we just saw, and leave a little gap there because I want to do another example of that other one, the power rule. So if we had the function 1, that's just a constant, right? This is telling us when we take the derivative, it becomes 0. And so that's why in that previous one, that's why I wasn't trying to harp on that because I wanted to say this first. In the previous one, the 1 just went away because it just became 0. And that should make sense. If we think about this as the slope of the tangent line, right? A constant function is just a horizontal line. Right, there's the function 1. The slope of that line is 0 everywhere. And so that's what this is telling us. Right, if we have a horizontal line, the slope is 0. That's literally what f being constant and f prime being 0 means. I feel, is that helpful? Maybe let me write that down. So let me just say the slope of a constant function is 0. That's what this rule is telling us. Is it okay? All right, I just wanted to do one other power rule example to show you how that comes up sometimes. Do I have enough rule to sneak it in there? I think I do. You might want to write it somewhere else. Sorry if you don't have enough room right here. So it comes up, let's do another power rule one. When we have radicals or this is not going to be enough room, is it? If I write small, I'll be able to fit it in here. I apologize. You might need to fit it in somewhere else. Let's say we had the function. I'm also skipping ahead a little bit. Where's the sum rule? Yeah, the sum rule. Okay, so real quick. One of the questions that Josh had asked was, what happened with the x squared and the plus 1? So those are two separate things. And I just want to point out that that was the sum rule. So let me just talk about that real quick. This says when you have two separate things being added and you want to do the derivative, you just look at their individual derivatives. Right, so the example we just looked at for that would be like this. That x squared plus 1. Right, if you want to do the derivative, and let me remind you of this notation. If you want to take the derivative of the function, you just take the derivative of each of those pieces. And when we take the derivative, we get f prime. And so this is just an application of the sum rule because we had two separate things being added, and what the sum rule says is you can just look at them separately. And when we looked at them separately, one was a power rule and one was a constant rule. Can mention one other thing. There are questions about that. I'm going to slide up in just a second. Maybe we should talk about, let's do the linear function one too, because that's an application of both these things, right? So let's pretend we had f of x is, I don't know, 2x plus 8. It's a straight line with slope of 2. What this says is the derivative is 2, right? It just tells us that whatever the slope is, you get that as the derivative. Could someone explain why that makes sense? Practically speaking, why is it that the derivative of a line is just the slope?
This is going to stay the same regardless.
Yeah, that's right. So, and who else was going to follow up with that?
I was just going to say because on a linear function, like on a straight line, the slope is always the same.
Yeah, exactly. If we looked at 2x plus 8 as something like this, no matter where we look at the tangent line is the line itself, right? If I was going to draw a tangent line, let me do it in another color. It's just going to be right over top of the same line because it's just a line, right? And so a way to think about that is like the slope is how the line is changing. It tells you how the line is changing, and it's always changing at that same way because it's just straight, right? But the other thing I was going to point out is this is an application of a couple different rules. So if you took the derivative of mx plus b, you take the derivative of mx and b separately. That's the sum rule, right? Mx is a power rule. We got the constant rule in there with b. And so you can see how that we start putting rules together, basically, is what we're trying to do. These snowball, and you just look at each individual piece is what the idea is, and you combine all these different rules together. Questions so far? Slope is how is line. Slope is how lines changing. You guys are gonna let me get away with that? No one's gonna say anything?
Like, I was just looking at it just now, and I was like, "What?"
Slope is how lines change. Let me try that again. Slopes describe how lines change. How's that? Man, sometimes I feel like, yeah, they're on it, they're asking questions, and then like other times I write something that doesn't make any sense, and just let me write it. No, I'm just kidding. Okay, so I just want to do one more power rule example. That's where we were. So what if we had something like this? 1 over x times square root of x. We can think about that as a power rule by thinking about that as x to the minus 1. I'm sorry, put a plus in between there. That's what I meant to do. Plus x to the 1/2. Right? 1 over x doesn't look like a power rule, but when you write it as x to the minus 1, it does look like a power rule. Right now, they both look like this. They both are kind of in that general form. Square root of x doesn't look like that, but when you write it as x to the 1/2, it does. And now we can apply the power rule just by kind of thinking about that a little bit differently. Right? And when we do it like that, the derivative ends up being bring down the power, subtract 1 off the power. Bring down the power, subtract 1 off the power. I'm sorry that got a little jumbled there. Hope you had somewhere to put this with a little more room. What I'm trying to point out is 1 over x's or 1 over x raised to a power or radicals you can think of as power rules. There's more complicated ways to do them, right? We just did 1 over x in a very complicated way right here. We just did this one a second ago. Here we were doing 1 over x the hard way, and we had to do fractions. We did the limit, blah, 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 blah. What I'm saying is, let's just think about that as a power rule and make our lives easier. Do people see how that power rule went, though? I didn't do the details because I was running out of room, but I brought down the power, multiplied it, and then subtracted 1 off the power. Is that okay? Good. All right, we're gonna end with the power rule. We're gonna kind of slowly go through these over the next several classes, 2 or 3 classes. The thing I'm gonna ask you to do on Wednesday is the power rule. Okay, there's gonna be homework in Wednesday that relates to the power rule. And so just know that this stuff is gonna be in there. And what I'd like to just finish class with are the 3 examples that use the power rule. Right, so you can see the next couple pages are kind of broke down by different types and whatever. And let's just finish off with some power rule examples. Maybe I'll think about a couple and then ask you to think about a couple. So, super easy ones like this, polynomials, they always use the power rule, right? Because they're just x's raised to whole powers, and so we're going to use that power rule. The one that I've kind of skipped over so far that we should hone in on is the constant multiple rule. So let me just slide up real quick and show you this one real quick. This constant multiple rule, have we done it already? Not really. Can you guys hear my dog in the background, or is that just me?
Okay. Very faintly.
Okay, good. Dog is very loud. Super distracting for me. Let's see here. We're almost there. Oh, with the constant multiple, it's just telling us if we have a constant times a function and we take the derivative, we just ignore the constant and we take the derivative of the function. Do you see how that's showing that here? It says like C doesn't change. What changes is G turns into the derivative, right? So you just kind of like ignore the constant and you just work on the function. And so that applies here, because if you had something like this and you take the derivative, you ignore the number and you just focus on the x cubed is what I'm sort of saying. I'm going to erase this in a second because I don't know if I have enough room for that, but I'll kind of show some of the details here. Right, so something as simple as a polynomial like this one actually involves a bunch of the rules up there. It involves, we're going to use the power rule because they're all raised to powers. We're going to use the constant rule because they have some constants in front of them. We're going to use the multiple rule. And the sum rule. So a bunch of things come into play, and it's not hard stuff. If you've never seen this before, it maybe does seem. But what I'd like to sort of preview in the future is this stuff should become kind of second nature, and it's not terribly difficult. It's easier than doing the limit, that's for sure. All right, so let's do this one. So when we take the derivative, we bring down the power, and we subtract 1 off the power. I'm going to do this one kind of carefully. Notice how the 16, right? This is one people get confused about. It's 16 times x to the 1. And so you bring down the 1 and then subtract 1 off the power, and then you end up with x to the 0. And then when you take the derivative of 9, it just becomes 0 because that's the constant rule. And so let's keep simplifying it and let me know if this looks okay. This becomes 4x cubed, 6x squared, 16x to the 0. What is anything raised to the 0?
One.
Number 1. And so the thing that we really want to take away from this is when you take the derivative of x, it becomes 1. That's something that people get confused on, right? So this is 4x cubed plus 6x squared minus 16. That's the final derivative. And one of the things I'm trying to point out here is when you take the derivative of x, you just get the number 1. not 0. Oftentimes people think you get 0 when you take the derivative of x. You bring down the power, which is 1. You get x raised to the 0, which is 1. So it's like, oops, sorry. It's just 1 times 1, which is just 1. Right? Maybe even let me write the details. You have 1x to the 0, which is 1 times 1, which is 1. Right? And is everyone okay with this notation? This d over dx? I mentioned it last class, but I haven't mentioned it again. Maybe I'll just slide up and point out to you where that says it. It says it right here. Right here, all the different ways that we can say take the derivative. And one of them is d over dx. And I wrote that right there, right? D over dx means take the derivative with respect to x. So that's a notation I'll use when I'm doing like, hey, I'm about to take the derivative of this, and then the next step will show the derivative, right? That's right. We're trying to think about this like writing a book almost. So I'm saying when I write down something like this, I'm saying I'm going to take the derivative of x, and then the next step is I did it. Okay. Thoughts about the power rule on that one? Does that seem okay? Okay. I think I'm going to stop here. I think this one will be a good one to start with next time, and then I'll let you try the last one. So I'll sort of refresh your memory with that first one, and then I'll let you try the second one, and then we'll start digging into some more rules. Questions about anything? There is a minute left. I'm happy to stick around if you've got some homework questions or anything about the notes you want to chat about. Anything about anything here? All right, cool. Well, we'll start with that next time. Let me know if you need anything in the meantime. Remember, I've got office hours over the next 3 days, so pop on in if you want to chat about this stuff. Love to do that. Have a good one.
Thank you, Professor.
Thank you.
So we use the power rule on polynomials. What you'll see in this next one is we also use the power rule on radicals. And so the first thing we need to remember is how we can change radicals into powers, right? And so let me just remind you about that. I'll remind you about this from some previous class, like pre-calc or something, right? When you have the eighth root of x to the b, you can change that into the exponent x to the b over a. Does that kind of ring a bell? I hope that rings a bell for most people. And if not, it's okay, but just know that now and let's apply it here, right? So on this example, square roots, they don't have a number there, but there's really like a 2. Right? You guys remember that, how there's no real number written there, but it's kind of like a hidden 2. And so with that in mind, we can change this into x to the 1/2 plus x to the 3/2 minus 6 using, this idea here that we just looked at. Is that okay? See that? And then it becomes a power rule because we just have x raised to a power, and so we can just apply the power rule, which is really easy to do. We have to do a little bit of fraction stuff, but it's nice. Can I clarify something about changing radicals to exponents?
So could you remind me why there's a hidden 2?
It's kind of like, when you write the variable x, it's kind of like there's a hidden 1 there, but you don't necessarily write it. Or when you write the x, there's like a coefficient 1. It's just like for some reason, the square root is so common that you just drop writing a 2 there, and we just assume that if there's nothing there, there's a 2. Now, it could be other roots, right? So there could be like cube roots, for example. So if we had the cube root of x, my goodness, come on. That would be like x to the first. We would change that to x to the 1/3.
Okay, that makes sense. Thank you.
Is that okay? Yeah, so it is important to remember though, square roots have it's a 2th root. I know that sounds weird. The 2nd root instead of like the 3rd root, the 4th root, the 5th root. Those things sound better. Instead of saying the 2nd root, we usually just say square root. But now we're just, we're prepared to use the power rule really easily. We need to know how to subtract with fractions, but that's not a huge deal. And so when we take the derivative on this one, you just bring the power down, subtract 1 off the power. Bring the power down, subtract 1 off the power. And then remember, when you take the derivative of the number 6, that's the constant rule, and we just get 0. And so you don't have to write that, but I'm just being clear about where that 0 or where the 6 went. And then when we do the subtraction in the powers, it just becomes 1/2 x to the minus 1/2, 3/2 x to the 1/2, and then we don't have to write the 0 part anymore. And I'll just kind of take it one step further. We almost never want to leave negative exponents. So I've got a negative 1/2 there. And so I'm going to fix that by writing this as 1/2 times 1 over square root of x. Right? So you bring it down into the denominator, and then I just change it into the square root. I guess I don't need to do that. Let me, I'll just write it as 1 over x to the 1/2. Maybe that's a little more clear. And then the other one you can just leave alone. That one's fine. It's got a positive exponent. We don't have to do anything there. You're welcome to change them into square roots if you want. You don't have to, though. Thoughts about that power rule?
On the homework, there's this one question where it shows, I think it's 5 to the x power.
Yeah.
How would you use the power rule to figure that out for the derivative?
I'm going to do that. I'm actually going to do an example of that in a second. So that's not a power rule, right? So a power rule is a variable raised to a number. That is a number raised to a variable. It's kind of the opposite. And so that is going to be, that's an exponential. Here's the exponential rule, right? So that actually looks like this, which we're going to use this concept for. And I'm planning on doing, I noticed there was a couple of those in the homework as well, and so I'm planning on doing one of those right here. Other thoughts?
Yeah, why don't you leave the negative half exponent like as so? Why do you multiply it?
It's generally, it's like a convention that when you have a negative exponent, it creeps people out. I don't know. It's just like a convention. I'm not probably going to be super picky about it. But you should be able to know or understand that when you have a negative exponent, you can make it into a fraction, or if you have a fraction, you can flip it over into a negative exponent, right? It kind of works both ways. And just again, the convention is usually people don't like negative exponents. I'm probably never going to take points off for that, but it is something you need to know how to do, especially since we're going to need to use that concept right in the next problem. Other thoughts before we look at the next one? I'm going to actually ask you to try that next one. But can I clarify something about this before you do?
I do have one more question, sorry.
Yep.
What do you do with the 6 at the beginning?
So when you take the derivative of a constant, it becomes 0. So that was one of the things we looked at last time. When you have a constant function and you do the derivative, it just becomes 0. Like this example that we looked at here. Or we saw it in this problem right here. This 9 became a 0 from the constant rule.
Okay, thank you.
Right, so anytime you have something without a variable and you take the derivative, it just goes away, it becomes 0. Because the rate of change of a constant is 0, right? It doesn't change, it's constant by definition. Like literally the word constant means it doesn't change, right? And if we're looking at the rate of change, there is none there. That's one way to think about it. Other thoughts? Keep them coming. This is good stuff. Okay, so we want to use the power rule in the next one too. And so the first step here is to switch these things into powers. And so I'd like you to think about that using the concept we just thought about, right? So that the root is going to turn into an exponent thing using this kind of idea. And then the two fractions are going to move into the numerator and become negative exponents. So just take a second and think about what this equals. And then I'll write down the right answer just to make sure we're all on the same page, and then I'll give you a second to actually take the derivative. And if you feel good about this, you can just go ahead and do it. But right, so the x squared in the denominator becomes x to the minus 2, using that idea we just saw. And then the 1 over square root becomes x to the minus 1/2. Right, it's this is kind of doing the opposite of what we just did a second ago. Right.
3/2.
And then the last part, yeah, is minus x to the 2/3 actually. Oops.
2/3. Oh.
Right. Notice how. Oops, that's not what I meant to do. Notice how the a goes in the denominator here. Is that okay? People see how that translates into that? All right, do the power rule on that thing. So then bring the power down, subtract 1 off the power, and that's how we get the derivative. So I'm going to kind of slowly write the answer down in case people are lost or they want to check their work. But I'm going to write down the details. So bring the power down, subtract 1 off the power. When you bring down the minus power, it makes it negative, right? And we just need to be careful about fractions and negatives, right? So we have like a -2, -1, for example, right? Be careful to note that that's -3. Let me move this down a little bit. Right, when you do the fractions, -1/2, -1, again, that becomes more negative, right? So that's -3/2. And then 2/3 -1 makes it into a negative, right? Becomes a -1/3. And so I'm generally okay with an answer like that. You know, in problems like this, that the idea is like, do you know the power rule? Not, can you remember everything from past classes and stuff like that? But past class things are important. And so it's nice to just be able to recognize that this becomes this, for example. And we could change those into radicals if we want. Not super concerned about that. So, you know, either of these things is a fine answer. Okay, what do you think? Feel okay about the power rule? Most of the homework tonight is using the power rule. We have to have a really good handle on the power rule because it needs to be one of those rules that's just like a quick thing we do, because there's definitely more complicated rules that the power rule is going to be inside of. So this is one of those things that we just need to be kind of good at. Not that you're necessarily there, but you know, if there's not like an understanding of what we're doing, let me help you clarify it.
We just -1, right?
You just subtract 1 off of the powers. Yep. And so if it's a fraction, you're subtracting 1 from it. Like sometimes people have questions about that. Let me just zoom in on this one, for example. Right, 2/3 -1 becomes 2/3 -3/3. Right, you just turn the 1 into whatever the denominator of the other one is over itself. And then you end up with 2 - 3 is -1/3. So that's where this came from, for example, right?
Do you know if on WebWork, if we have to type it, like, for example, like -2/3 x to the -1/3 power, do we have to put it under the bottom of a fraction, if that makes sense? Like, will it not accept to a negative power?
That's a good question. WebWork may not like negative powers, but I think if it doesn't like it, it usually tells you that in the warning or whatever in the error. It'll say eliminate negative exponents.
Perfect. Thank you.
Yeah, other thoughts or questions, keep them coming. I just want to look at the exponential rule. That was what someone else was asking about. And there's a couple questions at the end of the homework that have the exponential rule. And then we can talk about tangent lines. And then I think you'll be well prepared to do the homework. And again, we need to extend the homework, that's fine. But if you just look at the next couple homeworks, I have the homework for next week posted as well. There's just a lot of problems because these rules can manifest themselves in so many different ways. So we just need to be able to expose ourselves to lots of different problems. And if we understand the rules, they're kind of quick problems. But if we don't understand the rules, 20 problems becomes like a very daunting task. So anyway, that's why I don't want to like push this one necessarily to next week. I know we're just getting the homework on the day it's due. If we want to push it back a couple days, we can do that. But I'm looking for a good faith effort from people tonight. Okay, let's look at this exponential one. No questions before we do that? We're going to look at this one here.
Can you go back up for a second?
And as we get down to this one, I'm actually going to do a second example that looks more like the homework. So let's do a second example. Just want to write this down so you can leave some room for it. That's more kind of what the homework looks like. And so we'll do a simple example with the 1/3 e to the t, and then we'll do this more complicated one. Is everyone okay with moving on? Okay, so we're looking at the exponential rule. Let me slide up to that. Oh, and actually, this is what I was doing at the start of class. I just took all these derivative rules and I put it in their own document, but then of course I just screwed that up. I'm trying to avoid scrolling so much. I know that's annoying to look at. So I'm just going to open up the derivative rules and have them separately. And as I mentioned, it's nice if you have hard copies of this stuff, just to have these rules out somewhere and not having to flip around in your pages constantly. So what this tells us is if we have the function e to the x and we take the derivative, it stays the exact same. It's the most amazing rule in all the derivative rules. You do nothing to an exponential function, which is super interesting if you think about what that means. That means at every location on the function e to the x, let's remind ourselves what e to the x looks like. Kind of does this thing, right? Every location on this graph that I'm kind of dotting out, I'll do it in red, the slope of these tangent lines equals the function value, right? So let's say this is the point A. The slope right here is e, whatever e to the a is. Just a very interesting property. But what you need to know is when you take the derivative of e to the x, it just stays the same. It's very nice, and it's kind of an interesting thing. And so if we go back to this example then, this derivative is as easy as it gets. G prime of t just stays the same. But that only applies to e raised to a power. We have other rules for different exponential functions. So is that one okay? I mean, you literally just don't do anything to the function. It just stays the same. The other one is a little bit different. So this one I wrote down below here, I'd like to look at this second one. There's a couple in the homework, or at least one that looks like that. That is this rule then. Right? We have some other number raised to a power. Oh, as a reminder, in case you're not familiar with e is a number, it's an irrational number. It's approximately 2.72. But it's irrational. It kind of it's like pi. It continues forever. And so this is a specific base for an exponential. If we have any other base, like 2 to the x or 4 to the x, etc., then we need to use this concept. And so notice how part of it stays the same, right? So when you have the derivative a to the x, the a to the x stays the same over on the right. You just need to add this extra component, which is the natural log of the base. And the reason that it kind of works here too, if you do ln e times e to the x, ln of e, these are inverses, and so that just equals 1. And so technically it works with e to the x too. It just stays the same as when you do that. That's kind of how to think about that. And so if we look at that example then, this 4 times 2 to the x example, and we take the derivative, zoom in on this. I'm going to use that rule, and again, you might just have it out and reference it. The 4 just stays the same, and then we multiply by natural log of the base, and then the base stays the same. And then we do the same thing with the other one, natural log of the base times the same exponential. Questions? Seems okay? Okay. I'm going to skip ahead a little bit. So this is currently page 26, right? Can we please skip ahead to page 31 just for a second? Because this is talking about the equation of the tangent line. And a lot of the future homeworks, including the current homework due tonight, ask you to do that. And so we should just probably jump to here if that's okay. Does everyone see where we are? Page 31. Let me just leave this highlighted. So, you know, as a reminder, this is kind of using the idea that I wrote a second ago, right? We're going to use these ideas that I started with. We're going to think about the slope of the tangent line, and then we're going to use the equation of the line there, right? So that's why I wanted to touch on that in the beginning here. Let's draw a hypothetical function like we always do. I like to draw this same function over and over again. And let's talk about the point A. And then here is f of A, right? And I really wish I had not put this stuff so close. So let me try this. So the tangent line, when we draw this tangent line in red, and we think about the slope of that line, when we take the derivative and plug in the point A like I wrote down previously, that'll tell us the slope of the tangent line. And so, as I mentioned, and if you looked at the homework, lots of the questions say, find us the equation of the tangent line, right? So we want to find the equation of that red line. And what I'm saying so far is when you take the derivative, what else do we need for an equation of a line? We need the slope, and we also need some point to put in there. Right, so let's remind ourselves how to write the equation of a line. The point slope form is usually the easiest thing to use here. But you can use any one you want. But you need a point, so you need some point x1, y1. And you need a slope. Usually you call that m. And you'll remember way back when you learned this formula, right? Y minus y1 equals m times x minus x1. And so I've already told you how to get the m. And now all we need is a point. And the way you get the point is you're usually given an x value. You plug that x value into the function to get the y value. So I'm going to let everyone sort of catch up writing that down, and then we can look into this next example. Questions so far? Is that okay? See what I'm trying to say there? You guys remember that a form of the line? You're welcome to use this form too. Lots of people like y equals mx plus b. That's fine if you want to do that. But the problem with this is you need to find b, which you can do. It just takes a little bit extra work. And so usually the previous one is just an easier thing to do. Everyone with me? So here's the procedure then. If we want to do this, we follow these 3 steps. You calculate the derivative. In the homework, it's using either the power rule or the limit definition. You plug whatever point you're interested in into the function, right? This is going to tell us the slope. Okay? And then we need a point. And the point we're going to use is the value we're given, a, and then f of a, right? This is going to be our x1, y1 that's going to go into the formula. And then that's it. You just plug the numbers into the formula. And so I think I'd like to do the example using the homework question, because we're not quite ready to do this example, because this example uses the product rule and we have not yet covered that. So I'd like to, and it'd be better to do a homework problem anyway, right? So I'd like to switch to the homework problem, but are there questions before I change the page about that?
Just one thing to clarify. You're saying that the derivative of f of a is exactly equal to the slope?
It's equal to the slope of that red line that I drew right there. Yes.
Okay, perfect. Thank you.
So that's the kind of thing I was trying to clarify at the start of class here, was like, you're usually given a function, f of x, right? You can take the derivative, which will also have an x in it, and then plugging numbers into that derivative tells you slopes of tangent lines. And so that's just differentiating the 3 things, f of x, f prime of x, f prime of a of x oftentimes look very similar to people, but they're 3 very different things, is what I'm trying to convey here. And we can look at another example here in a second. Other questions about what I was trying to say in the notes before I just get rid of the notes and go to the homework question? So let's finish off this limit derivative homework question. And let's see, I'm just trying to decide if I've got enough room here. I think I'll just erase some of this, or maybe I'll just zoom in and it'll be fine. I really want another color though, darn it. Oh, I can't get another color. Okay. So let me just go ahead and tell you that when you take the derivative of this one, it's a power rule, and so we get minus 2x plus 3, right? So that's what's going to go into the G prime box. If we want the slope of the tangent line, we need the slope. And so when we do G prime of 2, that's what we were talking about here. We just plug 2 into the thing we just found. Right, so it'd be minus 2 times 2 is minus 4, plus 3 is minus 1. So that's our slope. Is that okay? So that's the slope of the line tangent to the point at 2. And so I'm just trying to follow the procedures I just had, right? So we have the derivative, we plugged in the point to get the slope. And now part C is trying to get you to do the next part, right? It's trying to get you to get a y value, and so that we can then use the y value to calculate the derivative. Right, so part 3, I'll do in green. Let's find the y value. We need to use the original function, so it's going to be this. So it's going to be -4 plus 6 is 2 plus 3 is 5. And so this is a y value. And so then the last part is just to write the equation of the line. And so I'm going to do that at the bottom, but are there questions about what I've done so far? Is that okay? Took the derivative, plugged in the value to get the slope. We found a y value, and now I'm going to write the equation of the line through the point we're given 2. So the x value is 2. Oops, I didn't mean to write 2. I meant to write 2 there. And then the y value is 5. All right, the 2 is just what we were given in the problem. And the 5 is what we calculated right here. And we already found the slope. The slope was -1. Where did we get the slope from? The slope came from right here. And then we're just going to plug it into the line formula, right? So we're going to do y minus y1 equals slope x minus x1. And so that is y minus the y value of 5 equals the slope of -1 times x minus the x value.
Can you scroll down a little bit?
I cannot. I was wondering if someone was going to have an issue with that. This is just the bottom of the page. I wonder if I could do that. Is that helpful? So I'm glad someone asked this particular question, because this is doing each one of those steps we just talked about, right? Calculate the derivative, find the slope, find the y value, plug it into the formula. It's breaking it down to each step there. Other problems don't do that. Other problems just say, find the equation of the tangent line. But you're still going to want to do each one of these steps. So I would say, going back to this problem, either reviewing the video as it's being recorded now and these notes should help guide you on the other